Hi, and welcome back to part 3 of our Toon Shader exploration. If you haven't already watched parts 1 and 2, I highly suggest you check it out. There's a lot of great content. All right, so as we left off, we have a two-tone Toon Shader. We have an ambient lit or unlit. We have a diffuse lit, and then we have a specular lobe. And this shader is available here at this link, and or you can find it in the description later. So what we want to do now is add rim lighting. What is rim lighting? Well, let's go to our explanation. Roystan has an amazing tutorial that I've been going off of for this series, and he explains that rim lighting is the addition of illumination to simulate reflected light or backlighting. So essentially, because our shader is a little limited in that we don't have stuff like diffuse reflection or object reflection, we just only take in consideration the lights in our scene. We only look at the stuff that's shining onto our object and not stuff that's reflecting off of other things. So we simulate that effect by using rim lighting. It's just a way of making this the scene feels that little bit more dynamic. I'm sure if you've played Breath of the Wild or have any sort of interest in those types of games, you see the rim lighting is happening along the edge of the character. It's very subtle in this example here, but if you play through the game, you can see just how it gives that watery type of look. It's able to show when there's light in the scene, but it's not directly directly viewable through the specular reflection. It still is a way of showing like, hey, this character is still lit. It's very bright. So just wanted to go and just show a few examples of just games that I love that use this effect, this Toon Shader effect in some respect. The OG Jet Grind Radio. Absolutely love this game. If you've never played it, please try it. There's plenty of anime-inspired games. This looks like a Naruto, Gekko Ninja Taisen, and it's very well-made, cel-shaded fighting game. I believe this is the remake of Zelda Wind Waker, my absolute favorite Zelda game. And of course, as I said before, plenty of anime-inspired games. Dragon Ball Z, of course, again. Breath of the Wild used the great effect. I believe. I've played. I don't think I've played this game before. I can't tell you what this is. But all these games use that hard, soft two-tone shading to great effect. And so just wanted to just give you some good examples of where you can find this sort of thing. It's mostly used when you're using assets with well-defined geometry, if that's the best way of saying it. The more complicated your geometry is, the harder it is to get the lighting to play off of it properly. So a lot of models made for this. There's actually a very good talk done by Arc System Works that goes into the detail of this. The name of the game is Guilty Gear. I think it's Xrd. And this game, they use this game to more or less pioneer their anime-inspired 3D. So as you see here, these are actually 3D models here. You can see like the hard, soft two-tone shading here, and they just go meticulously in every frame of animation is done to make sure that the normals are facing in the right direction so that you don't get like weird lighting artifacts. And yeah, it's just the more complicated your geometry is, the harder it is to use this Toon Shader to good effect. So without further ado, let's add our rim lighting to this. Sorry, I just love gushing about games, and since you're here to learn, you might as well learn about all the cool stuff in the industry. All right, so the most important thing with the rim lighting is that it is dependent on your surface normal and your view direction. We don't really take lighting into effect in this, or at least not at first. So if you see this rudimentary implementation, we take the dot product of our V vector, view direction, and our normal vector, and we invert it. or take the 1 minus of that, so that we, instead of getting the inside lit, we get the rim lit. And this effect is not just useful for rim lighting, it's useful for any sort of effect where you want that outline. The 1 minus gives you that outline, and it's very useful for when you're trying to do cell shading. You can easily calculate an outline for your character by using the 1 minus of your view normal dot product. So let's add that to our scene. We have our V vector here somewhere. I believe this is V. View direction, normalized, is V. So let's label this, because we're good programmers. We're good programmers. We label our variables. There we go. So we want our n.v. So I'll add a dot node to our chart, and we'll take our n normalized and we dot it with our v normalized, and we'll get how much our view direction is aligned with our normal, surface normal. So as always, we can debug this using the vector merger, or sorry, not the vector merger, but the color merger. And we're going to merge the R, G, and B channels of this output, and we're going to feed that to our output here as a nice bypass. So if you can see, this is n.v, and as you can see, as we, independent of our view direction, so I'm dragging around and nothing changes because it's our view direction that drives this color, is the brightest when our view direction is aligned with the surface normal. So if we can look at other shapes, where our view direction aligns with the surface normal, we get the brightest coloring. So we want the opposite of that. So we can use the 1 minus to get the, I'd call this the inverse, but it's not really the inverse. It's just 1 minus the value. Since we're using normalized values, we're between 0 and 1, it's logically the inverse. As you can see now, we have the rim lit and the center is unlit. And we want to tunify this value, don't we? So what we want to do is we can quantize it, but there is a bit of a better way. But I'll show you what happens when we quantize with the step function. This is very useful for your outline effects. So we'll take our 1 minus value, and we'll call this our rim threshold. Oops, we need a float. And this is our quantized rim intensity. So this is the intensity of the light of our rim light effect. And we quantized it, or at least we would have before I accidentally deleted it. So let's add it back to the scene. It's got to be careful with your backspacing here. Sometimes it will delete your node if you don't have the proper focus on the text bar. So this is our quantized light, let's call it rim light intensity. Easy. All right, so let's feed that into our color merger, and we should see the effect. Boom. There's a good reason for that. If you remember back in part 1 and 2, when we're using the cutoff, we want to use a value that's non-zero. Otherwise, everything that's 0 is going to be lit. It's greater than or equal to, I believe. So let's use a rim intensity of 0.6. A little around half. If you want a stronger outline, you can increase it. If you want a weaker one, you can decrease it. Or if you want a weaker one, you can decrease it. If you want a stronger one, you can increase it. Easy, right? So actually 0.6 is giving me a really good one. I played around with this earlier. You can see the shader ball with its complicated geometry doesn't really play well with this rim effect. You just have to be careful about your geometry. You have to take your geometry into account depending on what effects you want to use for the best visual look. But what we can do at the very least is try and remove some of the underside lighting. So if you look at the sphere, not only is the parts that would be lit are lit, but the part that will be unlit are lit as well. So let's modify the shader here to remove the parts that should be unlit. We don't want to rim light the unlit parts of our model. So we've already calculated that before using n.l. That's how much our light is directed towards our surface normal. So what we can do is actually, according to Roystan, he uses a very interesting technique here. So he uses POW. So basically you have some thresholding value. That's our rim. Was that our rim cutoff? We can use our quantization cutoff as our threshold for this. And we raise our n.l, so how much our normal points towards the light source, to the threshold of the rim, or how much we want to, what's the word I'm looking for? Amplify that n.l. It'll concentrate the light to a smaller and smaller area of the object. And then we multiply that by our 1 minus rim dot product. He calls it rim dot, but it's actually 1 minus the dot product here. Just one careful thing to keep in mind. So let's implement this equation here using our node editor. So we have 1 minus rim dot, and since we're good programmers, we label everything we do. It's n dot v. And then this is 1 minus n dot v. And now what we want to do is we're going to get our POW function. And we're going to raise n.l to the POW of rim intensity. Or in our case, we can use our rim cutoff, but let's call that rim intensity for now. And let's get our n.l. We don't want the quantized version because we do want this to kind of trail off in areas where it's not supposed to be so strong. Otherwise, you get that kind of not so good looking shader ball effect. So this can be our, this doesn't really have much of a value. I'll call it the rim factor. Going back to our specular factor, just give it some name that kind of explains what it does. And now we can multiply this by our rim intensity. Whoa. So we call n.v our rim dot product. We multiply it by our rim factor. And I think it's safe to call this rim intensity. And so let's see what this does. Instead of using our quantization approach, now we're using our POW-based approach. And if you can see here, we're starting to get somewhere. Replace this guy, and here is our rim lighting effect. Now we're only lighting the lit parts of the model. But, Nick, hey, this doesn't look very toony. That's why we quantize. So rather than just quantize the entire lighting calculation, we want to use that POW function and the rim intensity. So maybe this was actually wrong. I don't think this is the right way to go about it. We can keep the rim intensity for our first half of our equation, but we also want a cutoff factor that we use to control just how far away from the edge of this lit part of the edge of our model do we want the rim lighting effect to go away. So as you can see, we can modify the intensity, and that kind of concentrates our rim lighting to a smaller and smaller area. So 0.1 will give us a very strong rim lighting effect. Let's try 0.6 again. It looks really good. So now we're going to add another float here, and that's going to just control how strongly we quantize this value. So we'll take the rim intensity. This goes here. And hey, we already had the name right from the beginning. Don't you love when that works? All right, so now we're going to reattach these. And if you can see here, now we're going to add a nice strong cutoff of 0.5. And as you can see, now we have, I'd call that a proper rim lighting effect. We can adjust both of these coefficients to control the extent of it. So if I reduce the intensity, it might be a bit of a misnomer because reducing the intensity kind of makes it more intense, you know? But, and we increase our rim cutoff. So the intensity controls how far along the horizon the rim effect extends. The cutoff, on the other hand, controls how far into the circumference or into the radius the rim effect extends. So 0.1 will give us a very strong rim effect. This is a bit of a better view. So let's make that, let's give it a higher and higher and higher and higher cutoff, and you can kind of understand where I'm getting at here. So I actually really like 0.6 and 0.4 for our rim cutoff and rim intensity respectively. I think that gives us a very nice effect. We can look at other objects and kind of see how that plays into the lighting calculation for these objects as well. You can look at the cylinder here. We only really get the rim effect along the lit part at the top of the object. The plane, it's not going to look well on the plane because it's flat. The shader ball, on the other hand, actually it's starting to look a bit better. You still get a few artifacts here just based on the geometry of the shader ball and how the light will, that n.l gets calculated because the normal vector is pointing towards our camera right now, or pointing towards the light source and our camera. Yeah, this doesn't look too bad. n.v times n.l. So it needs to be the camera and the light source. So now I believe we've gotten this to a point where I think it's good to plug this into the rest of our lighting calculation. So we can remove our debugging color merger. We're going to add one more color, that it will be our rim lighting color. As usual for the other effects, you can use your light information's color if you want to use the actual lights in your scene. I'm using my own color inputs just for the sake of demonstration, being able to show these different effects more effectively. I just have more control over the lighting by putting in my own color inputs. But you have your light information here, and you can just use this color here for all of your color calculations. You may want to tone it down for the ambient and the diffuse and have different cutoffs for that. So basically you'll scale this to different values based off of different values just based off of what you want to do. So you'll use the color here and you'll scale it and you'll scale it, and that'll give you different lighting inputs. It'll give you different factors for the ambient and diffuse lighting, but it'll still play well together in your Toon Shader, and I believe it'll work with multiple lights in your scene because now you can do that lighting calculation. It'll do this lighting calculation for each light and add everything together at the end. So now that we know what we're doing here, here is where we do our final surface color calculation. Here we add our specular and diffuse. So I think here all we need to do is add our rim lighting calculation. So we have our specular diffuse. We add in the rim light, add rim plus spec plus diffuse plus ambient. And that will go to our output. Right now we just need to scale. This is our rim lighting calculation. And we're going to add a color 3 for our rim light color. Let's just make sure this is properly capitalized. And we'll use a scale node. And we're going to scale the rim light to our intensity factor. So scale this, input here, and the output goes here. And I believe, what's not done here? What's looking wrong? Sorry, I'm going to go to desktop. We're saying the build, the input RGBA from the fragment is not connected. Oh, duh. And boom, looky here. And I believe this is our full shader. We can look at different effects. As you can see here, now we have our ambient, we have our diffuse, we have our specular highlight, and now we have the rim lighting effect. It looks so cool. I love to see whatever anybody wants to use this effect for, or if you want to modify it, I'd love to hear just different ways we can modify this effect and just give more dynamic dynamic applications of this. I think you following this tutorial, you'll have the tools to not only make different outline effects, but also make like really cool view direction dependent effects. So as always, if you've liked this video, please give us a like, consider subscribing. We have plenty more content coming out. And most importantly, we just love to see what you guys want to do with this engine. This is here for the world to consume and make cool things with. So have a nice day, and I hope you enjoy the rest of your day.